Neuroaesthetics is a relatively recent subdiscipline of empirical aesthetics. Empirical aesthetics takes a scientific approach to the study of aesthetic perceptions of art, music, or any object that can give rise to aesthetic judgments. Neuroaesthetics received its formal definition in 2002 as the scientific study of the neural basis for the contemplation and creation of a work of art. Neuroaesthetics uses neuroscience to explain and understand the aesthetic experiences at the neurological level. The topic attracts scholars from many disciplines including neuroscientists, art historians, artists, and psychologists. Overview. Neuroaesthetics is a field of experimental science that aims to combine psychological research with aesthetics by investigating the perception, production, and response to art, as well as interactions with objects and scenes that evoke an intense feeling, often of pleasure. The recently developed field seeks, among other things, the neural correlates of aesthetic judgment and creativity. It is argued that visual aesthetics, namely the capacity of assigning different degrees of beauty to certain forms, colors, or movements, is a human trait acquired after the divergence of human and other ape lineages, rendering the experience of beauty a defining characteristic of humankind. One core question for the field is, for instance, whether art or aesthetic preferences are guided by a set of universal laws or principles. Additionally, the evolutionary rationale for the formation and characteristics of these principles are sought. It is believed that identification of the brain circuitry involved in aesthetic judgments can help pinpoint the origin of these responses. Approaches of study. Researchers who have been prominent in the field combine principles from perceptual psychology, evolutionary biology, neurological deficits, and functional brain anatomy in order to address the evolutionary meaning of beauty that may be the essence of art. It is felt that neuroscience is a very promising path for the search for the quantified evaluation of art, with the aim of discovering general rules about aesthetics. One approach is the observation of subjects viewing art and the exploration of the mechanics of vision. It is proposed that pleasing sensations are derived from the repeated activation of neurons due to primitive visual stimuli such as horizontal and vertical lines. In addition to the generation of theories to explain this, such as Ramachandran's set of laws, it is important to use neuroscience to determine and understand the neurological mechanisms involved. The link between specific brain areas and artistic activity is of great importance to the field of neuroaesthetics. This can be applied both to the ability to create and interpret art. A common approach to uncover the neural mechanisms is through the study of individuals, specifically artists, with neural disorders such as Savant syndrome or some form of traumatic injury. The analysis of art created by these patients provide valuable insights to the brain areas responsible for capturing the essence of art. The aesthetic enjoyment of individuals can be investigated using brain imaging experiments. When subjects are confronted with images of a particular level of aesthetics, the specific brain areas that are activated can be identified. It is argued that the sense of beauty and aesthetic judgment presupposes a change in the activation of the brain's reward system. A crucial aspect of research lies in whether aesthetic judgment can be thought of as a bottom-up process driven by neural primitives or as a top-down process with high-level cognition. Neurologists have had success researching primitives. However, there is a need to define higher-level abstract philosophical concepts objectively with neural correlates. It is suggested that aesthetic experience is a function of the interaction between top-down, intentional orientation of attention and the bottom-up perceptual facilitation of image construction. In other words, because untrained persons automatically apply the object identification habit to viewing artworks, top-down control to reduce this habit may be necessary to engage aesthetic perception. This suggests that artists would show different levels of activation than non-artists. Aesthetic responses to different types of art and techniques has recently been explored. Cubism is the most radical departure from Western forms of art, with the proposed purpose of forcing the viewer to discover less unstable elements of the object to be represented. It eliminates interferences such as lighting and perspective angle to capture objects as they really are. This may be compared to how the brain maintains an object's identity despite varying conditions. Modern, representational, and impressionistic art has also been studied for the purpose of explaining visual processing systems. Yet aesthetic judgments exist in all domains, not just art. Theories of pioneers. Zeki's laws of the visual brain. Zeki is a professor of neuroaesthetics at the University College of London. He sees the viewing of art as an example of the variability of the brain. Thus, a neurological approach to the source of this variability may explain particular subjective experiences as well as the ranges of abilities to create and experience art. Zeki theorizes that artists unconsciously use techniques to create visual art to study the brain. How such creations can arouse aesthetic experiences can only be fully understood in neural terms. Such an understanding is now well within our reach. He proposes two supreme laws of the visual brain. Constancy. Despite the changes that occur when processing visual stimuli, the brain has the unique ability to retain knowledge of constant and essential properties of an object and discard irrelevant dynamic properties. This applies not only to the ability to always see a banana as the color yellow but also the recognition of faces at varying angles. Comparatively, a work of art captures the essence of an object. The creation of art itself may be modeled off of this primitive neural function. The process of painting, for example, involves distilling an object down to represent it as it really is, which differs from the way the eyes see it. Zeki also tried to represent the Platonic ideal and the Hegelian concept through the statement, "Forms do not have an existence without a brain and the ability for stored memory," referring to how artists such as Monet could paint without knowing what the objects in order to capture their true form. Abstraction. This process refers to the hierarchical coordination where a general representation can be applied to many particulars, allowing the brain to efficiently process visual stimuli. The ability to abstract may have evolved as a necessity due to the limitations of memory. In a way, art externalizes the functions of abstraction in the brain. The process of abstraction is unknown to cognitive neurobiology. However, Zeki proposes an interesting question of whether there is a significant difference in the pattern of brain activity when viewing abstract art as opposed to representational art. Ramachandran's 8 Laws of Artistic Experience. Leonardo Ramachandran and his fellow researchers, including William Hurstein, developed a highly speculative theory of human artistic experience and the neural mechanisms that mediate it. These laws combine to develop underlying high-order concepts of the human artistic experience. Although not all-encompassing, as there are undoubtedly many other principles of artistic experience, the theorists claim that they provide a framework for understanding aspects of visual art, aesthetics and design. Although testing of these principles quantitatively may provide future evidence for specific areas of the brain responsible for one kind of aesthetic appeal, the theory faces substantial philosophical and historical objections. Peak shift principle. This psychological phenomenon is typically known for its application in animal discrimination learning. In the peak shift effect, animals sometimes respond more strongly to exaggerated versions of the training stimuli. For instance, a rat is trained to discriminate a square from a rectangle by being rewarded for recognizing the rectangle. The rat will respond more frequently to the object for which it is being rewarded, to the point that a rat will respond to a rectangle that is longer and more narrow with a higher frequency than the original with which it was trained. This is called a supernormal stimulus. The fact that the rat is responding more to a super rectangle implies that it is learning a rule. This effect can be applied to human pattern recognition and aesthetic preference. Some artists attempt to capture the very essence of something in order to evoke a direct emotional response. In other words, they try to make a super rectangle to get the viewer to have an enhanced response. To capture the essence of something, an artist amplifies the differences of that object, or what makes it unique, to highlight the essential features and reduce redundant information. This process mimics what the visual areas of the brain have evolved to do and more powerfully activates the same neural mechanisms that were originally activated by the original object. Some artists deliberately exaggerate creative components such as shading, highlights, and illumination to an extent that would never occur in a real image to produce a caricature. These artists may be unconsciously producing heightened activity in the specific areas of the brain in a manner that is not obvious to the conscious mind. It should be noted here that a significant portion of the experience of art is not self-consciously reflected upon by audiences. So it is not clear whether the peak shift thesis has any special explanatory power in understanding the creation and reception of art. Isolating a single visual cue helps the organism allocate attention to the output of a single module, thereby allowing it to more effectively enjoy the peak shift along the dimensions represented in that module. In other words, there is a need to isolate the desired visual form before that aspect is amplified. This is why an outline drawing or sketch is sometimes more effective as art than an original color photograph. For example, a cartoonist may exaggerate certain facial features which are unique to the character and remove other forms which it shares, such as skin tones. This efficiency prevents non-unique features from detracting from the image. This is why one can predict that an outline drawing would be more aesthetically pleasing than a color photograph. The viewer's attention is drawn towards this single area, allowing one's attention to be focused on this source of information. Enhancements introduced by the artist more carefully noted, resulting in the amplification of limbic system activation and reinforcement. Grouping. Perceptual grouping to delineate a figure from the background may be enjoyable. The source of the pleasure may have come about because of the evolutionary necessity to give organisms an incentive to uncover objects, such as predators, from noisy environments. For example, when viewing ink blots, the visual system segments the scene to defeat camouflage and link a subset of splotches together. This may be accomplished most effectively if limbic reinforcement is fed back to early vision at every stage of visual processing leading up to the discovery of the object. The key idea is that due to the limited attentional resources, constant feedback facilitates processing of features at earlier stages due to the discovery of a clue, which produces limbic activation to draw one's attention to important features. Though not spontaneous, this reinforcement is the source of the pleasant sensation. The discovery of the object itself results in a pleasant aha revelation, causing the organism to hold on to the image. An artist can make use of this phenomenon by teasing the system. This allows for temporary binding to be communicated by a signal to the limbic system for reinforcement, which is a source of the aesthetic experience. Contrast. Extracting contrast involves eliminating redundant information and focusing attention. Cells in the retina, the lateral geniculate body or relay station in the brain, and in the visual cortex respond predominantly to step changes in luminance rather than homogeneous surface colors. Smooth gradients are much harder for the visual system to detect rather than segmented divisions of shades, resulting in easily detectable edges. Contrast due to the formation of edges may be pleasing to the eye. The importance of the visual neurons' varying responses to the orientation and presence of edges has previously been proven by David H. Hubble and Torsten Wiesel. This may hold evolutionary significance since regions of contrast are information-rich, requiring reinforcement and the allocation of attention. In contrast to the principle of grouping, contrasting features are typically in close proximity, eliminating the need to link distant but similar features. Perceptual problem solving tied to the detection of contrast and grouping is the concept that discovery of an object after a struggle is more pleasing than one which is instantaneously obvious. The mechanism ensures that the struggle is reinforcing so that the viewer continues to look until the discovery. From a survival point of view, this may be important for the continued search for predators. Ramachandran suggests for the same reason that a model whose hips and breasts are about to be revealed is more provocative than one who is already completely naked. A meaning that is implied is more alluring than one that is explicit. The generic viewpoint, the visual system, dislikes interpretations which rely on a unique vantage point. Rather, it accepts the visual interpretation for which there is an infinite set of viewpoints that could produce the class of retinal images. For example, in a landscape image, it will interpret an object in the foreground as obscuring an object in the background, rather than assuming that the background figure has a piece missing. In theory, if an artist is trying to please the eye, they should avoid such coincidences. However, in certain applications, the violation of this principle can also produce a pleasing effect. Visual metaphors. Ramachandran defines a metaphor as a mental tunnel between two concepts that appear grossly dissimilar on the surface, but instead share a deeper connection. Similar to the effects of perceptual problem solving, grasping an analogy is rewarding. It enables the viewer to highlight crucial aspects that the two objects share. Although it is uncertain whether the reason for this mechanism is for effective communication or purely cognitive, the discovery of similarities between superficially dissimilar events leads to activation of the limbic system to create a rewarding process. Support for this view is highlighted by the symptoms of Capgras delusion, where sufferers experience reduced facial recognition due to impairments in the connections from the inferotemporal cortex to the amygdala, which is responsible for emotions. The result is that a person no longer experiences the warm fuzzy feeling when presented with a familiar face. A person's glow is lost through what is suggested as due to the lack of limbic activation. Symmetry. The aesthetic appeal of symmetry is easily understandable. Biologically, it is important during the detection of a predator, location of prey, and the choosing of a mate, as all of these tend to display symmetry in nature. It complements other principles relating to the discovering of information-rich objects. Additionally, evolutionary biologists suggest that the predisposition towards symmetry is because biologically, asymmetry is associated with infection and disease, which can lead to poor mate selection. However, departures from symmetry in visual art are also widely considered beautiful, suggesting that while symmetry may explain the judgment that a particular individual's face is beautiful, it cannot explain the judgment that a work of art is beautiful.